So let's look at this problem, and as always, we always read our problem first. So what is asked of us here is use the method of sections, that's very important, to calculate BC, FG, and CG. So first thing I should do is identify where those are located. So BC would be right here, then FG would be right here, and last but not least, CG would be right here. And I have two choices now. I can just cut the left side, which is probably what I will choose to do, because look at it, it's a cantilever and I don't have to worry about support reactions that way. Or if I want to make my life complicated, I can also use the second cut here, but then I would have to calculate all my support reactions first. So I think that would be a waste of time for us. So first thing I do is I draw my free body diagram for my cut 1. So let's do that. So cut 1 and draw the cut so that I can use it as a free body diagram for my identification of the relevant points and such. So I have this system here, and I also have this force. And let us bring down our forces. 1000 Newton. That's 1 kilonewton actually. And again, remember that we cut the system. And let's identify our forces. And originally, we always assume everything to be in tension. And we are dealing here with BC up there, CG, and GF. And now I can look at my system here first and identify what unknown I want to start with. So let's evaluate it. The sum of the forces in x is not a good idea because I have 3 unknowns acting in the x direction. That would give me 3 unknowns in one equation. That is not good. The sum of the forces in y would actually work very well because I have only two forces that act in the y direction. So that is the part here in CG and the 1000. So I can do that without any lever arms. So maybe that's the one I start with. So let's say I want to find CG by the sum of the forces in the y direction being equal to 0, upwards positive, and 0 is equal to plus CGY minus 1000 Newton. So I know that CGY is equal to plus 1 kilonewton, and the plus tells me that I assumed correct, so therefore it's actually going in the upwards direction, which means it's in tension. So I got that figured out, and now I need to, of course, convert from CGY to CG, and I have to do that using dimensions, but I guess we're lucky in this case because it seems to be a 45-degree triangle. So therefore CGY is equal to CGX is equal to 1 kilonewton, and the CG itself is equal to the square root of 2 times 1 kilonewton. And that is equal to 1.414 kilonewton. So I already calculated that. In fact, that is something that we were asked for, so I can already double underline that. And now I can calculate my other forces. So let's see which one we want to do next. Sum of the forces in x doesn't work. We already talked about this. So I need to use the sum of the moments. And let's look at which point we want to take the sum about. So I have two options here. I can either find GF or BC first. If I want to find BC, I would have to take the sum of the moments about which point? Exactly about point G here, because the line of action of this force and the line of action of this force pass through that point, and therefore it disappears. However, similarly, if I want to find GF, I could also take the sum of the moments about point C, right? So let's look at that. So point C is right up here, which would be outside of the cut, but it would be here. But BC and CG have a shared letter, the C, and therefore it disappears, right? So I'm going to repeat that again. I said it when I introduced the method of sections. If there's a shared letter, usually they meet in that point. So BC and CG meet, but also CG and GF meet. And so again, if I want to find BC, I take this point with the shared letter G, and I take the sum of the moments about that point. But if I want to find GF, then I need to take the sum of the moments about C, which is BC shared with CG letter, right? So they both share that letter C. So I just have to decide now. Let's see which one I'm gonna go with. So I guess because it's an educational problem, I'm gonna pick the one that's up here, right? So the one where those two come together, because that is outside of the cut, which often is problematic for students, and it's always good to practice the things that are problematic. So let's do that. So let's take the sum of the moments about point C. Sum of the moments about point C is equal to 0, counterclockwise positive, and 0 is equal to, I start with my unknown, GF multiplied by 2 meters, right? So the height of the structure is 2 meters. 2 meter. And now I have to decide what the rotational sense is. So if I assume GF in tension initially, it turns counterclockwise, so therefore it's positive. So positive GF. And then I also have the 1000. Well, so I'm going to make that a kilonewton in this case. So kilonewton, 1 kilonewton. And that is multiplied by, be careful now, 4 meters, right? So 2 times 2 meters. So let's write it down this way, 2 times 2 meters. And my rotational sense is turning about that point this way around. So that is counterclockwise. So therefore it's also positive. So that's positive. And now I can solve this for GF. So GF actually happens to be negative 1 kilonewton, so that's 4 kilonewton divided by 2. All right, so that is effectively 2 kilonewton. And the negative tells me that it's actually in compression, since I assumed tension originally. So GF technically, if I go back in here, so let me take a faint green pen and say that GF is actually going in with 2 kilonewton here. And now I could use the sum of the forces in the y direction, sorry, in the x direction, to put this in equilibrium with this and this. And let's actually give that a try. So again, it's an educational problem. So now I can use the sum of the forces in the x direction being equal to 0, positive to the right, and 0 is equal to minus 2 kilonewton plus the horizontal component of CG, and we calculated that before. So CGX is 1 kilonewton, right? So we have that given here. So 1 kilonewton, and that was actually in tension, so we were correct there. So it's plus to the right, 1 kilonewton, and then plus BC. And you can also call that BCX, and that is assuming that it's in tension. And so therefore BC is equal to 1 kilonewton in tension. So I assume correct, right? Because the answer is plus here. And that, by the way, is also a result. So I'm double underlining that. Similar to my 2 here, that was also a result. And now I solved the problem. So let me go in here with green and let's agree that this was 1.41, 1.414, and BC here was equal to 1 kilonewton. So now we can look at the entire system or the entire problem again. And we solved for our 3 member forces here by using the cut 1. We could have used the cut on the other side, and I encourage you to do that because you probably want to be able to calculate support reactions for your upcoming exam, and you also want to be able to practice the method of section here. And by the way, you can also use the method of joints to work your way in here and to validate your results. So you will easily have a tool to find out if you are right or wrong, pretty much to check your own work. And I encourage you to do that for problems that are as small as these ones. So you just find the internal forces or the member forces by using the method of joints and the method of sections. And that will help you to gain confidence and solve more of these problems. Let's solve another problem. Let's look at this method of sections problem. So what are we asked here? Let's look. So method of sections and AB, BF, and EF. Let me identify those. So AB would be right here. BF would be right here. And now there's a trick. There's EF here. And you would think, hey, if I cut through all these members at the same time, I cannot use my method of sections because I'm cutting through effectively 4 members, right? 1, 2, 3, 4. But note that EB is a zero force member. And if you don't see that, then that can be problematic in an exam because you would probably trip over your understanding of that. And that could make your life difficult. But here, EF doesn't exist, so I'm erasing it for you. And now the problem is effectively like before, but for good measures, we can now go through that exercise, or actually I'm leaving that up to you, and I will solve the next problem for you or with you. So let's look at the next problem. And here we're gonna calculate the members CD, CH, and HI. So I have to identify those. CD would be right here. So CD is right there. CH would be right here. And HI would be right there. So I have 2 options now. I can either make this cut here on the left, or I could do the same thing here on the right. I'm not sure which one is easier yet. I have to evaluate that. I would say that I'm going to take the cut number 1 here and not number 2, simply because I only have one support reaction to deal with. So I'm going to have to calculate that support reaction RFY first, because that's the roller. So let me do that. Let's calculate RFY first. RFY is done by the sum of the moments about point A being equal to 0, counterclockwise positive, and 0 would be equal to RFY multiplied by, let's look at it. So the distance from here to here horizontally is 4 meters, so multiplied by 4 meters. And then I also have to include all the other external forces, right? But before I do that, I need to set a rotational sense. RFY is turning clockwise, so that's negative. And now all my other forces, so 40 kilonewton. Multiplied by 2 meters. and that rotates counterclockwise, therefore it's positive. The 50 passes through the point of interest, so I completely ignore that, but I can worry about the 30 and the 30 here, so I have to include that. So 30 kilonewton, and that's the same one multiplied by 1.5 and by 3, right? So I have 1.5 plus 3, and that's in meters. And they both rotate the same way around, otherwise I couldn't have combined those, but they both turn counterclockwise, therefore that's also positive. And if you solve that, you will find that RFY is equal to 57.5 kilonewton, and that is positive, therefore we assumed correct. So here we have 57.5 kilonewton. So now I can easily work through my cut number 1. So let me just use that for interest of time. I'm just going to introduce my forces here in that direction, in that direction, and in that direction. So I can now use my cut 1. And in fact, what I will do, just to make my life easy here, I'm going to erase the other part of the structure so we can easier see what's going on. So all this is gone. And now I can use my sketch here. So to do that, let me bring down that force, and this force. And the easiest one to calculate is probably HI, right? So this here would be HI. This would be HC, and we have CD up there. And the easier one to calculate would probably be H1 by taking the sum of the moments about point C, because then CD and HC disappear and all I have to deal with is HI. So let's write down that equation. So I'm interested in calculating HI, and I do that by the sum of the moments about C being equal to 0, counterclockwise positive, and 0 is equal to HI multiplied by 2 meters. What is that lever arm? Let me show that to you. So that's the lever arm from here to here, which is 2 meters up here. And it's actually rotating counterclockwise, so therefore that is positive. Now I have to include all the other ones. So let's start with the 50 kilonewton, which also has a lever arm of 2 meters. So 2 meters is turning also positive. Then I have the 40 kilonewton, which has to be multiplied by 4 meters. And that is also turning counterclockwise, so therefore positive. And last but not least, I have RFY. So RFY, but keep in mind we already solved this to be 57.5 kilonewton multiplied by 6 meters, right? 6 meters. And that is turning clockwise, therefore it's negative. And I can now solve this for HI by just rearranging the equation, and HI would be 42.5 kilonewton positive, which means it's in tension, or we assumed correctly. So yes, this here would be equal to 42.5, or I just double underline my result here. So now I solved that one. How do I find the other ones? For example, the next easier step probably would be to calculate CD, right? So let's look at CD, and I can do that by the sum of the forces in the y direction, because CD is the only one with a vertical component that is unknown, that is left. So upwards positive is equal to 0. and 0 is equal to minus CDY, vertical component, minus 42.5 kilonewton, minus 50, because it's going down, kilonewton, minus 40 kilonewton, plus 57.5 kilonewton. And so now I can rearrange that to find my CDY, which is equal to negative 75 kilonewton. And that means that it's actually in compression. So, and that is only the vertical component, the Y component. So let's look at this again. So I have 75 going up here. So that's 75. And if you remember correctly, we actually had a distance of 1.5 meters. I erased that here earlier when I made my sketch, but I have a distance here of 1.5 meters. And so my actual length of CD, so LCD, is actually equal to 2 squared plus 1.5 squared, and then square rooted the whole thing, which I believe is equal to 2.5. So I have a length of 2.5, so I can use that now to use my relationship, my triangular relationship, right? So I can say that 75, I have to write this down here, so 75 kilonewton corresponds to 1.5 meters, just as CD in kilonewton corresponds to 2.5 meters. And therefore CD is actually equal to 75 kilonewton divided by 1.5 multiplied by 2.5. And that then is equal to 125. So 125 in compression. And that is a result again. So CD here now is equal to 125. And so I almost done. All I need now is my HC, and HC is only acting horizontally, but don't be fooled, there's also a horizontal component here. So I have to include that. So my horizontal component here technically is going in this direction, and let me fix the CD here as well. So remember that CD here is actually acting upwards. So that's going in this direction because it's in compression, but we already wrote that down below. But I now want to calculate CD horizontal, and I'm going to do that down here. So CDX is equal to 75 kilonewton divided by 1.5 multiplied by 2. That's the same similar triangle that I had before. And so CDX is actually equal to 100 kilonewton. So now I know what that is equal to. And if I look at the entire cut here, I know that this component here is equal to 100. And so the only two things that act in the horizontal direction is this 100 and this 100. Everywhere else I have nothing that is horizontal, so I know that HC is actually 100 to the right, and that would be in tension. So I'm not even bothering writing that down in an equation form, but this is 100 kilonewton in tension. And now I solved all my three forces, and I believe you have all the tools you need now to solve problems with the method of sections or with the method of sections approach. So let's recap this problem real quick. We started with calculating the support reaction for only one support because we only needed one side of the system. Then we found first the HI component because it was the vertical one that could be calculated by taking the sum of the moments about node C here, and that's reflected in this equation, which gave us 42. And since I now had only one unknown in the y direction left in CD, I was able to use the sum of the forces in the y direction to solve for the 75 in compression. And then I used that to calculate my horizontal component in CD, and that I could use to find HC. So it's a logical way through. And so the problem usually for students is not to solve these types of equations. The numbers are very easy and often they can also set them up. The problem is really to know where to start and how to start. And I say it again, it's very important to understand where to take the sum of the moments about to get started with these types of problems. But I believe you have now enough resources to study this material, and I wish you good luck solving that. However, let's take a look at the conclusion of the lecture.